All right. So I've got 8:35 down here. So I'm going to get started. This is COMP2804 Discrete Structures 2, and I'm Darrell Hill, the instructor. We're here on February 8th. So we're, first lesson past the test. So the answer keys are posted on Brightspace. Almost everyone wrote the same test because I accidentally submitted the same test for both sections. So you're section B. If you look on Brightspace, you're the section B, and almost everyone is. The only people who wrote section A were in the PMC from section A, but so yeah, test one. The mark should be back, they said, by Friday. Usually they're faster than that, but there's about 500 scantrons, so I don't know how long that'll actually take. But yeah, so assignment 2 is out, and it's not due till after the break. Technically, it's due on the Monday. I'm not allowed to make things due on the Sunday after the reading week, so it's due Monday at 11:59 p.m. I'm not sure if this is not the date on your assignment 2, I will change that. And I did release it earlier, and then I released an update with a bonus question. So question 9 is a bonus question. It's based on Euclid's algorithm, which we're going to look at today. Euclid's algorithm is it's pretty hard. It's pretty nasty. It's not hard conceptually, but the math that we have to walk through to prove it is going to be difficult. So we're going to start with some light stuff and then move to Euclid's algorithm. And then, so again, the bonus question, there is some useful stuff to learn there, but the bonus question, it is a bonus question. So if you don't quite understand everything about Euclid's algorithm, that's okay. Try to understand at a high level. Don't get bogged down into the details, even though I'm going to get bogged down into the details. Yeah. So any questions on anything, I guess? Yeah. Yeah, there's no official office hours during reading week. Unofficially, I don't know if you could wrangle somebody. I will most likely still have my office hours. So Thursday at 10 a.m. And I'll just go as long as, is somebody still there to ask questions. Other questions? All right. Okay, so we're going to continue talking about recursion today. And specifically recursive algorithms. So this is computer science. So we are most interested in applying this to recursive algorithms. So we're going to look at some algorithms. We're going to design some algorithms and see how recursion is really nice in terms of, even if we don't know a solution to a problem, we can actually still devise a recursive algorithm that works, sort of using the principles of induction and things like that. And then we can analyze them. So we're going to start with a problem. If you read the textbook, this is called the gossiping problem. So I don't know, I just changed the context a little bit to the message problem. So I'm going to let n be an integer that's at least 4, and we will consider n people. And these people are at their computer terminals or what have you. And every person, PI, has a message MI that they want to send to everybody else. Okay, so now in order to send their message, so to begin with, everybody knows their own message. And I want to end up, after running the algorithm, I want everyone to know every single message. So everyone else's message. So then the key is then, how do we exchange messages? Well, to exchange messages, PI and PJ will say connect or message each other or something. There's some sort of, either there's a phone call or, VPN, peer-to-peer, what have you. And once they do that, they can exchange every message they have. So that in that case, PI will learn all of PJ's messages, and PJ will learn all of PI's messages. Okay, so that is the context of the problem. And then what we want to do is we want to figure out how to get from table 1 here to table 2 here with the least number of messages. Right, so the most efficiently. Yeah. fewest connections, fewest messages, however we want to phrase it. I'll probably use those interchangeably. Okay, so does everybody understand the problem? Okay, so we're gonna, yeah. Yep, absolutely. So all your messages that you have, when you connect to somebody, you give them all. Yeah, exactly. Yeah. Any other questions, clarifications? Okay. So we're going to design an algorithm, and ideally we want to use the fewest connections. However, to start with, we're going to just go brute force. Brute force may not be the best, but it solves the problem. So what we're going to do is we're just going to have everyone message or connect to everyone else. All right, so how many connections or how many messages are there? Well, I have to basically, I have a set of n people and I have to take all pairs from that set. All right, so then that's n choose 2. So a connection is between 2 people at the same time and no more, no less. And if we expand out n choose 2, we get n times n minus 1 over 2. And this is, I guess it should be noted, this is big O of n squared, right? So it runs in n squared time, essentially. All right, so that is the brute force, guaranteed to work, maybe not the most efficient. So let's try a small example and see if we can do better. So we will start with 4 people, P1 through P4, and everybody knows their own message. And we will see how many connections we need in order for everyone to have everyone else's message. So we're going to use this sequence of connections. Well, to start with, I can just kind of start arbitrarily. So let's connect P1 to P2. Now P1 has P2's message and P1's message, and P2 also has P1 and P2's message. So every time there's a connection, both parties end up with all of the same messages. Okay, so now at this point, let's try P3 to P4. And now we have P3 and P4 both have message 3 and message 4. All right, now let's connect P1 to P3. And if I do that, so P1 has messages 1 and 2, and P3 has messages 3 and 4. So now P1 and P3 both have all of the messages. So we're almost solved the problem. All we have left is P2 and P4. So then the final connection, P2 connects to P4. And now everyone has every message, and my algorithm's done. Okay, good questions on that? Okay, pretty straightforward. So this solves the problem for 4 people. Yeah. And if we used our original brute force algorithm, which we didn't really think too much about, but we would have 4 people and we'd look at every single connection we can make. There would be 6 messages or 6 connections. All right, so we've improved it a little bit. The question is, can we now extend this a little more? Yeah. Yeah, somebody else asked me this too. So I have to dig into that a little bit. There is an exercise in the textbook that delves into that, but I didn't read it. So I'll have to get back to you on that. Yeah. So if we did this for 3 people, it would be sort of, yeah. I mean, if we have time, we can actually try it out and see if we get the same answer. It could be that, yeah, anyway. I'll have to figure it out. Maybe we'll have time to figure it out today. Other questions? Okay. All right, so we have a base case, right? So if we have at least 4 people, which we do, then our minimum is 4, and we can solve the problem for 4 people, and we can do it a little more efficiently than we did before. So now that we've solved the base case, we can attempt to make a recursive solution. Right, so what we're going to do for that is we're going to assume that we can solve the problem recursively for a slightly smaller problem. So if I'm solving a problem for n, I assume I can solve it for n minus 1. And then I'm going to use this solution to solve the main problem. Right, so very similar to how induction works, where we just assume that, our inductive hypothesis is true for a smaller problem. And then we use that to solve the bigger problem. So recursive algorithms work the same way. All right. And because we have a base case, that makes this a reasonable assumption, right? So that means our recursion is going to end. It has some sort of foundation on which to build. And yeah, so it won't simply just run forever. Okay, so at the start, every person PI knows only the message MI. Right, so we're extending our solution for 4 people more generally using recursion. So this is our starting point, and then we will consider this algorithm. We're going to start by connecting Pn minus 1 and Pn. Once we connect them, then Pn minus 1 knows messages n minus 1 and message n, and so does Pn. Okay. Now, we are going to use our assumption that we can solve the problem for a smaller group of people. So what we're going to do is use recursion to solve it for this smaller set. And the nice thing about it is, because we did this first step where I had message or person Pn message somebody in this smaller set, well, now message n is part of the messages that Pn minus 1 knows. So if we can solve the problem, if we, in some sense, consider these 2 messages to be the same message, we recursively solve the problem for n minus 1 people, then we can assume that after that recursive call that everybody here knows everybody else's message, including message n. All right, so then we make our recursive call. We assumed we can solve it, and then our recursive call works. So now everybody in the first n minus 1 people know all of the messages at this point. That makes sense? Okay. Yeah, we can use induction. So this is sort of an inductive proof. So we're not using the official, sort of induction algorithm, but the idea is the same. I have a base case, and if I can solve it, if I can solve this case using my recursive case, then it's like a row of dominoes, eh? Yeah. All right, questions? Okay, at this point, I'm almost done. I just have Pn who does not know all the messages. So I can simply have Pn minus 1 and Pn connect again. And now Pn knows everything. And everyone knows everything, and I'm done. And the algorithm was pretty simple. I had 1, 2, 3 steps. All right. How did this, how could I solve this same thing writing a for loop? It is possible. How would it work? I don't know. I just use this sort of magical idea that if I have a base case and I can assume that I can solve it recursively, then I can solve the main problem, then everything's just going to work. All right, so I really want to say yes, but I would say that is most certainly almost true. Maybe there's some exceptions I don't know about, but at the edge of computing, there's problems that are you really don't run into very often, but mathematically you can break a lot of these assumptions. So I want to say yes, and for probably most of the programs you're implementing, if you can implement it recursively, then you can also write a for loop. The for loop is going to be more complicated, and you'll have to understand the problem better. But a recursion is a good place to start. We'll talk a little bit about the trade-offs too, but yeah. All right. Okay, so if we write our algorithm for message, it looks like this. This would be the base case, right? If we have exactly 4 people, then we can solve the problem with this sequence of messages. Otherwise, we have Pn or Pn minus 1 call each other or connect to each other. we make a recursive call to the algorithm message on n-1 people, and then we have these guys talk to each other again. So here's our base case and recursive case. And what we want to do now is we've shown that it works, right? Using our assumptions, sort of loosely, a little informally, but we've convinced ourselves that it works. So let's now analyze it. So we want to analyze the runtime. Yes, the questions that people ask in person. The question was, is every recursive algorithm, are you able to make it into an iterative algorithm? And I tentatively answered yes, but again, I would say almost all of them can be, but there's might be somewhere on the edge of mathematics where you could provably show that there's a recursive algorithm that can't be made iterative. But yeah, so that's sort of my answer. For the most part, yes. Maybe there's exceptions. All right. Okay, so the runtime, now we want to write it as a recursive function. So we've looked at recursive functions before and we've solved them before. So we're just going to take our recursive function right from this pseudocode. So what we want to do is, well, we'll say that C of n equals the number of connections that we make solving this problem for n people. Okay, so this is our function and it counts the number of messages. We know that if we have 4 people, then we have 4 messages, right? So that I'm taking straight from this part of the recursive algorithm. I have 1, 2, 3, 4 messages here on an input of 4. So C of 4 is equal to 4. All right, so that's our base case. Now our recursive case, I want to count this part. So what I have to do is I have to say, well, there's 1 message called here and 1 message called here. The order is not so important when we're just counting. And then however many messages are called here, right? So I have 1 message here, 1 message here, that's 2 messages, plus my recursive call, however many messages are there. So when I write that recursively, I get, well, on an input of n, I make 2 calls. If this is for n greater than or equal to 5. I make 2 calls or 2 messages, and then I make 1 recursive call on a problem size of n-1. Okay, so a recursive function. Now we're back to sort of where we know exactly what we're doing. So what we're going to do is simply plug in some values, find a pattern, guess at a closed form, and prove it using induction. Okay, so we expand it out. C5 is equal to, well, I just plug my values into here, 2 plus C4, which equals 2 plus 4 equals 6. So that's where we get that. If I wrote out C6 now, that's equal to 2 plus C5, which is equal to 2 plus 6, which is equal to 8. And then I could write it out for C7 and do the same thing. It would be 2 plus C6, so I would get 10 here. So if I, after a few iterations, I start to see a pattern forming, and that pattern is, this increases by 2 each time. So that would sort of give me some indication that it's 2 times the power, or 2 times n. And if I play around with this, with this constant here, this additive constant, then I can find 2n minus 4. I could also write it as, 2 times n minus 1 minus 2, or something like that. There's alternate ways to write it, but this is my guess now for the closed form. Okay, so simple enough. Now I just want to prove it using induction. So I have my base case, I have my recursive case, I have a guess at a closed form. Now it's simple. I say, I'm going to prove by induction. So I have a base case, which is n equal to 4. And C of 4 is equal to 2 of n minus 4. So 2 of 4 minus 4, which is equal to 8 minus 4, which is equal to 4. So now my base case is true because that's what it is, right? So this closed form is true for this base case. Now I want to show that it's true here. So I'm going to, my inductive hypothesis, again, I'm going to assume it's true for Cn minus 1. So my assumption is that Cn minus 1 is equal to 2 times n minus 1 minus 4. And then I'm going to write down my my recursive function and plug that value in. Cn minus 1, 2 plus 2 times n minus 1. So this is 2n minus 2 minus 4. Right, so I'm just distributing the 2 over the n minus 1. These 2's cancel out, and I get 2n minus 4, which is what I wanted to prove. So in this case, the induction and everything else was quite simple, but the steps are still the same. All right. So yeah, so on an input size of n, I have 2n minus 4 messages with this algorithm. I don't know how it's solved, but I can solve it and I can analyze it. All right, questions? Okay. Easy enough. Oh, yeah. Where was I? Yeah. And yeah, I have it written out, I guess, slightly more neatly here. Okay. We will do another sort of fun example. I used to have a Towers of Hanoi app, but I wrote it in Java and it uses JavaFX, and I was trying to install that this morning, and JavaFX, it's a module system. I don't know. I have to Stack Overflow that stuff, and it took too long. So I couldn't get the app running, but I have I have the discount version here. Yeah. Yeah, there are. And I have a little GIF. I have a little GIF later. Yeah. So just to give you the general idea. Yeah. Yeah, I taught that class using JavaFX, and it's a real pain compared to when it was just bundled in with Java 8. But yeah. All right. So the Towers of Hanoi problem is as follows. It's rather a famous recursive problem. So the idea is I want to take all of these disks from peg 1 and move them to peg 3. I think I have labels. Did I not save these? Okay, so I'll just write this down. So this is my source peg. This we will call the spare peg, and this we will call the destination. So the idea is I want to move all of my disks from, really messed up there somehow. Perhaps I didn't save it. Okay, so I want to move all of my disks from the source to the destination. Okay, source, spare, destination. I can move the disks one at a time. I have to take one off the top and move it to another peg, and I can never put a larger disk on a smaller disk, right? So those are the constraints of this problem. And I want to take all of these disks and move them to the third peg, right? So I have one spare peg that I can use to sort of organize myself, and then somehow get all of these disks to the third peg. You can solve this with a for loop iteratively if you just understand the structure of it, but we're just going to solve it simply using recursion. Yeah. Move the disks one at a time. So those are the rules. So again, if we want to solve this recursively, we need to be able to solve the base case. well, base case is pretty easy. I want to move some single disk from a source to a destination. I have one spare peg, but I don't really need it in this case. Yeah, I can just move this straight from disk 1 to disk 3, or from the source to the destination, and I'm done. Now, when I do this base case, it could be that I had larger disks underneath all of these, and that's fine. As long as this blue disk is smaller than all of the current disks, I can still solve that problem. All right, so I have a base case, and now I just want to hopefully solve it recursively. There they are. I guess I didn't put them on the first line. Okay, so now I want to do the same thing, but I want to solve them recursively, solve this recursively. So what I can do is I can assume that I can solve a smaller version of this problem. So in other words, I can take this stack of disks and I can move it to one of the other pegs, right? So in this case, what I want to do is I want to take this stack and move it to the spare peg. And then I want to take my single disk. So let's see, assuming I didn't mess up the animation. Yes. So I'm going to do this. I assume I can solve that smaller problem. So that's somehow using the magic of recursion, that's done. I take my single disk from the source. That's so weird. I move it to the destination. And now again, I can solve this smaller problem recursively. But now I'm going to use this as my spare peg. So this is my source. This is my destination. So yes. What's that? Yeah. Yes. So yes, that's accurate. So when I did my first recursive step, this would be now the destination, and this would be the spare, right? So I'm going to move all of these to here. And I can, yeah. Of course, I don't show that. That happens magically when I just simply relabel the pegs. Then I do my base case. And then I again do my recursive case. Now this is the source, destination, and this is the spare. Okay, so we can write a recursive algorithm that'll solve this problem and then analyze it. Okay, sorry, is there anything else that's not clear about what we did there? Okay. Yeah, my animations are way out of whack. All right, so here's a little, there's no pegs, but you can kind of see how the algorithm would solve it for 4 disks, right? So we're never putting a smaller one on top of or we're never putting a bigger one on top of a smaller one. And we're sort of recursively, you could think of these as the recursive calls that are made. Okay, so now our Towers of Hanoi algorithm is, well, my base case, if I have one disk left and I've been given my source, destination, and spare, I simply move one disk from my source to my destination. Otherwise, I have n greater than 1. So I'm going to make a recursive call on n minus 1 disks. Now my spare is my destination, and my destination is my spare. Once I've done that, I'm going to move one disk from the source to the destination. And then I'm going to, again, move my disks from my spare, where I moved them initially, to my destination using my source as a spare. So that's the entire thing to solve this sort of complicated looking puzzle. Okay, so let's analyze that now. So h of n will be the function, which is the number of moves to complete the puzzle on n disks. Oops. So we know that in the base case, h of 1 Again, I simply take it right from my algorithm. I do one move. There should be a return here. Let's, yeah, and then we return. Otherwise, in my recursive case, if for n greater than or equal to 2, I have h of n is equal to, I make one recursive call, so h of n minus 1. I make one move, plus 1, and then I make a second recursive call, plus h of n minus 1. Okay, so if I group those together, I get 2h of n minus 1 plus 1. Okay, so then we're going to solve this. We're going to walk through a couple of the values and see what sort of pattern we get. We're going to guess at a closed form, prove it by induction. So h of 1 equals 1. H of 2 is equal to 2 times h of 1 plus 1. So that's 2 times 1 plus 1 is equal to 3. H of 3 is equal to 2 times h of 2, which is 3, plus 1, which is 7. H of 4 equals 2 times 7 plus 1, so that's 15. H of 5 is 31. So the pattern I'm going to guess here is that the closed form h of n is equal to 2 to the power n minus 1. Okay, so, all right, so then we want to prove that. I'll go through this a little more quickly. So in the base case, h of 1 is 1. So if I say h of 1 is equal to 2 to the power 1 minus 1, that's equal to 1. So the base case holds. Now my inductive case, h of n, I'm going to use this. I'm going to assume at this point that, so now my space is a little messed up, but I'm going to assume that h of n minus 1 is equal to 2 to the n minus 1 minus 1, right? So I'm simply taking my guess at a closed form, and I'm assuming it's true for a smaller problem set. So now I'm going to write this as 2 times h to the n minus 1 plus 1. I will plug these values in for h to the n minus 1. Let's write this up here. So this is equal to 2 times, I simply take this value, 2 to the n minus 1 minus 2, right? Because this 2 gets multiplied by the minus 1 plus 1. So 2 times 2 to the n minus 1 is 2 to the n. This minus 2 and plus 1 equals minus 1. So I have shown that that's how long it takes, or how many moves it takes to solve that problem. All right. How are we doing for time? All right, questions on that? Yep. Yeah, I just wanted to be clear, just because this makes mapping this to the base case easier. So I could have said here, if n is equal to 0, simply return without moving anything, right? What's that? Oh, okay, yeah. Why is it between them? The way it's written, if I didn't have this here, I would simply then when I move the big bottom disk, so I have to move all of the n minus 1 top ones, then I have to move the big bottom one, but that's not gonna that won't happen on these recursive calls because these are only on n minus 1 disks. So Yeah, the one disk is always excluded from the recursive call. Yeah. So I have to move that myself. Yeah.
It's like all the possible subsets. It's not empty.
Right.
That doesn't make sense because then we have every single element unknown itself at least once. Then every two elements known together at least once. And then three elements together at least once.
Ah, yeah, yeah. Yeah. No, that is kind of interesting. Yeah. So what he said was that you can think of this when we're moving the disks, 2 to the power n is the sum of the nth row of the Pascal's triangle. So it's the sum of all of the binomial coefficients, and that's all of the ways we can choose a subset from a set, which just so happens that now if we look at every recursive call, we're choosing subsets. That's probably not, I don't know if that's exactly 1-to-1. But yeah. 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 There might be something there. Yeah. It's interesting. You know, yeah. Worth thinking about. It's neat when you can make those kind of connections. But yes, there's yeah. All right. Yeah. Interesting observation. Other questions? Okay. All right. So those are the easy ones, and now we're going to get to the rough stuff. All right. So just to warn you, it's very detailed. I think I could feel the spirit of the other class being crushed as I taught this one. But, so yeah, just try and hang in there. Try and pay attention to the big ideas. I will try to maybe not over detail it, but the algorithm itself is interesting, and the history behind it is interesting because this was made by Euclid. It's an algorithm for finding the greatest common divisor, and this was 300 BC, way before computers. So it is in some sense one of the oldest algorithms that's still being used today. So yeah. The greatest common divisor. So if I have 2 integers, a and b, that are at least 1, the greatest common divisor is the largest integer that divides them both evenly. Right, so we can look at some examples of that. So if I have 75 and 45, I can look at all of the divisors of 75 and 45, right? So they both, 1 divides into them both evenly, 3 divides into them both evenly, so does 5, and so does 15, and that's it. Those are all the divisors they have in common. And of those, the greatest of those is 15. Okay. So yeah, another thing about the greatest common divisor of a number with itself is simply itself, right? So I cannot have a greater divisor if I'm, you know, say the greatest divisor of 40 cannot be greater than 40, right? So that sort of makes sense. So yeah. So how do we find the greatest common divisor of really large numbers? Right, so these are relatively small, but I could have, for instance, these 2 numbers. So again, the first attempt at it, we could try brute force. Brute force is, in this case, I would take the prime factorization of these numbers, right? So every number can be written as a product of prime numbers, because if the number is not prime, of course, it's divisible by some other number. So I can reduce it down to the root factors in some sense, which are all prime numbers. So I can write this number as 3 squared times 5 to the 1 times 13 to the 4 times 17 to the 2. So that means I can divide it by 13 4 times, I can divide it by 17 twice, etc. And then I can write down the prime factorization of this number. Some of these numbers that they have in common, particularly these ones. And of those, I can count how many of them they have in common, right? So I can say, well, this one has 4 3s as a factor, and this one has 2, so there's 2 3s in common. This has 2 5s, and this has 1 5, so there's 1 5 in common. This has 3 13s, and this has 4 13s, so there's 3 13s in common. So I take out all of the common factors, and that gives me the greatest common divisor of those two numbers. All right, so any questions on that? Everybody following? Okay, this is actually very, very hard to compute, right? So the prime factorization of large numbers is extremely slow. And there's a bunch of computer security. I don't know much about computer security, but allegedly, they use prime factorization in that. And the idea behind it is that it's very unlikely you're going to be able to factor this big prime or this big number. If you could factor it quickly, then you could bust a bunch of security. But yeah, so an integer with 1,000 digits will take thousands of years to compute using the prime factorization. Okay. So Euclid's algorithm for greatest common divisor sort of gets around this prime factorization. So yeah, what it does, yeah, it's fast and easy. So fast is, I mean, way faster than prime factorization. We'll see exactly how fast. Invented in 300 BC, around 300 BC, and it uses the modulo operation. All right, I want to make sure I don't run out of time. Okay, so modulo, if I take two numbers A and B and I take A mod B, it's the remainder of A divided by B, right? So this is, I guess, public school days. I divide 17 by 5, it goes in 3 times and I have 2 remainder, right? So that's the modulo function. So that means I can write my number A as some number Q times B, right? So that's the number of times B can go into A plus the remainder, right? So if I wrote this as, and I believe I do this, but I can write 17 as 3 times 5 plus 2, right? So how many times does 5 go into 17? It goes in 3 times with 2 remainder. So I can express the relationship between these 3 numbers can be expressed as this linear equation. Okay. Yeah, a couple, sorry? Yes, exactly. All of them are integers, so we want it to divide evenly. Yeah. So yeah, Q is an integer. It's the number of times B goes into A. And the fact that we have a remainder means that we can do this with all integers. The remainder, of course, has to be less than B. If the remainder was equal to B, then we would simply be able to divide B in one more time. And the quotient can be 0, that's fine, or greater. We don't do negatives. Okay, so yeah, Q is quotient, yeah. Okay, so some examples, 17 mod 5 is equal to 2, right? We talked about how we could express 17 is equal to, I believe I do this actually, 5 times 3 plus 2. So 17 mod 5 is equal to 2. 17 mod 17 divides into itself once, the remainder is 0. 17 mod 1, 1 goes into 17 times with a remainder of 0. 17 mod 19, or a number mod anything larger, simply gives me a remainder of 17, right? So that is How many times does 19 go into 17? It goes 0 times with 17 remainder. I think 0 is a special case. Divisible by, because it's technically divisible by every number. So, right. I don't think it's considered prime, but I would have to look that up. And it might depend on how you want to define prime. Yeah. What's that? Right. Yeah, but in this case, Q doesn't have to be a prime number. It could be, I mean, I can say, what is 8 mod 2? Or even, 2 is a prime number. That's a bad example. 8 mod. Oh, no. 8. What's that? Not necessarily. I can have, let's say 8 and 10. So, 88 mod 10 is equal to 8. And Q would be 8 in this case. R would be 8. A is 88. And B is 10. And none of them are prime. Yes. Yes, of course. Yeah. Yeah. Every number can be written as a prime number. Yeah. Or sorry, a product of primes. Yeah. Can we have so A divided by a negative number? Right. Yeah, in some languages, yeah, I think it depends on the language. I think it might be implemented slightly differently in different languages. So yeah, that's a valid point. We are using mod in our own special way that solves this problem, but there are it can be defined on negative numbers. Yeah. You mean in a computer? It is done, I think it is. I would have to look that up. I think it simply subtracts B from A as many times as it can until it has some value less than B. So I think that's how, because yeah, I mean, CPUs are technically not that efficient. So in some sense, the algorithm Euclid on the assignment might be closer to what an actual computer does, although the computer does it very, very fast. I think that's how they do it. Yeah, there might be some special operation. Other questions? Okay. All right. So yeah, we can express it as A equals Q times B plus R. Okay. So now the algorithm is as follows. Yeah, maybe it's for the best that I run out of time. I don't get too bogged down into details. So I want to find the greatest common divisor of A and B. And we're going to assume that A is at least as large as B, if not larger, and B is at least 1. So I compute the remainder using the mod function. And if the remainder is 0, I'm going to return B. My claim is that in this case, B is the greatest common divisor of A and B, which probably makes sense if you consider it a little bit. If the remainder is 1 or more, then I'm going to recursively call Euclid on B and the remainder. All right, so if the remainder is at least 1, as we talked about, this is inaccurate. So B must be greater than R. The remainder cannot be equal to B because if it is, then I can simply divide B into A one more time. Okay, so that's it. That's the entire algorithm. So let's attempt to run it on our example of 75 and 45. I think, using prime factorization, we can get to, if we break these down into a product of primes, we get 3 times 5 squared and 3 squared times 5, and they have in common 3 times 5, which is 15. So the greatest common divisor of 75 and 45 is 15. But let's see how Euclid computes it. So in the first step, I take A mod B and find the remainder. 45 goes into 75 once with 30 remainder. R is not 0, so I don't end at this point. So now I call Euclid on B and R, which is 45 and 30. Again, I call the mod function. So 45 divided by 30, 30 goes in once with 15 remainder. Again, R is not equal to 0, so I make another recursive call. In this case, I'm going to, again, A mod B, but in this case, B divides into, or 15 divides into 30 twice evenly, and I have a remainder of 0. Once I have a remainder of 0, I simply return B, which in this case is 15. Okay. It worked in this case. Quite clever to come up with, because it's not obvious that this should work. But questions on that? Okay. All right. So we want to prove that it's correct and then analyze the runtime. Both are very, very detailed. We'll try and keep it a little as high level as possible. So to argue that Euclid is correct, what we want to do is use induction. So we have to argue that it terminates. In order to use induction, I have to be able to rank the calls, the recursive calls that we make. So to prove that it terminates is kind of easy, right? We can prove that it, yeah. All right. Okay, so yeah, I have 2 separate things to prove. First, I'm going to prove that Euclid terminates. If it terminates, I can use induction. And then I want to prove that it's correct by proving that it returns the greatest common divisor of A and B in both the base case and the recursive case. So I think I mixed these up a little bit. Okay, I think my slides are slightly out of order. Let me just see what I do prove here. Okay. So complicated, even I get confused. All right, so we got to prove both of these things. So we want to prove that it terminates. We could skip that part. I think it seems obvious. Basically, you can rank them by, every time I make a recursive call to Euclid, it's on smaller and smaller numbers. If either of these numbers if B gets down to 1, then I'm going to, the remainder will be 0. So that's sort of the high level proof that it terminates. Again, I think it's obvious because the numbers keep decreasing in value. That's the high level idea. If that slide does pop up, we'll probably skip it. But the other thing I want to prove for it to be correct, I want to prove that this returns the greatest common divisor of A and B in both the base case, so when R is equal to 0, and the recursive case. So in order to prove that, when R is equal to 0, I want to show that the greatest common divisor of A and B is B, because that's what Euclid returns. If the remainder is greater, I want to prove that this returns the greatest common divisor of B and R, and also that the greatest common divisor of B and R is the same as the greatest common divisor of A and B. So if I do that, then I can show that this actually returns the correct answer to this problem. Right, so hopefully that makes sense. So we're going to start by proving just this one and this one. So we'll start by proving that if there's no remainder, the greatest common divisor of A and B is B. And if there is a remainder, then the greatest common divisor of B and the remainder is the same as the greatest common divisor of A and B. All right. So these are the two things we want to prove. The first one I think is pretty obvious. Right. I can write A, if R is equal to 0, I can write A as equal to QB plus 0, which means it's simply written as Q times B. The greatest common divisor of these two numbers is B because it cannot be any larger than that. B is the greatest common divisor, or the greatest divisor of itself. Okay, so case A is kind of obvious. If there's no remainder, B is the greatest common divisor. That should make sense. So now we move on to the second one, which is a little more complex, is that these share a greatest common divisor. So to prove that, I want to show that all of the common divisors of A and B are the same as the common divisors of B and R. If I do that, then of course the greatest must also be the same. Okay. So I'm basically going to take an arbitrary divisor of A and B and show that it's also a divisor of B and R and vice versa. Right? I need a bijection. So I have to argue that all of the common divisors of A and B, and all of the common divisors of B and R are the same. And to do that, I'm going to show that if a number D is a common divisor of A and B, then it is also a common divisor of B and R. And then also, if I have a common divisor of B and R, then that's also a common divisor of A and B. So the bijection, if I can do that, show a bijection, that means that they have every single divisor in common. And that means the greatest divisor they also have in common. Okay. Questions? Yeah, this is where it gets worse before it gets better. Okay, so to show the first one we want to prove is that if I have a common divisor of A and B, then it's also a common divisor of B and R. I can basically say that, well, if it's a common divisor of A and B, then I know it's a divisor of B. I just need to prove that it's also a divisor of R. So I'm going to rewrite this linear equation as R is equal to A minus Q times B. And then my assumption is that D is a divisor of A, so I can write A as a multiple of D, right? So I can write A as D times some number A prime. Also, D is a divisor of B, so I can write B as a multiple of D. So I say B is equal to D times B prime, some number B prime. So now I'm just going to substitute these in for A and B in this equation. So once I do that, I can see that they both have a common factor of D. I can take that common factor out. These are all integers, so this results in an integer times D, which is also an integer. So then D is a divisor of R, right? Or R is a multiple of D, same thing. Questions? Yeah, all right. So R is a multiple of D, so we've shown the first part of this. Now we want to show the second part. We want to argue the other direction, is that if we assume D is a divisor of B and R, we also must show that it's a divisor of A and B. Well, we already know it's a divisor of B, so we just need to show that if D can divide B and R, it can also divide A. Again, we're going to look at this linear equation and do something very similar. D divides into B evenly, so I can write B as D times B prime. D divides into R evenly, so I can write R is D times R prime, right? This is our assumption. And then if those two are true, then I can write A as just by substituting B, D's in for B, and this in for R. And I can take out the common factor of D. So again, these are still all integers. So this equation is an integer and D is an integer. So D is a divisor of A. Okay. So what have we shown here? We've shown that, yes, we've argued that all of the common divisors of A and B are the same as the common divisors of B and R, which means that if I take all of the greatest common divisors of A and B, those are the same as the greatest common divisors of B and R. All right. So B is true. Now what we're going to do is argue that our recursive call to Euclid returns the greatest common divisor of B and R, which is actually the same as the answer to our problem. All right. All right, so we have now lemma 1 that we're going to use in the proof of Euclid. Here's where we prove that Euclid terminates. So yeah, I think we went over the high-level proof of Euclid terminating. I'm not going to get into all of the detail. I think we can all agree that it terminates. Seems pretty obvious. It counts down. Even if it was just reduced by 1 each time, we would eventually get down to 1 divided by 1, which would return, right? Because R would be equal to 0. So Euclid terminates. Now we can use induction on this recursive call. Okay, so if the remainder is equal to 0, we return B, which is the greatest common divisor of A and B, as we discussed earlier, right? Simply because there cannot be a common divisor greater than one of the numbers. So B is the greatest possible. And then we will rank our calls on the first number A. So when I make my recursive call to Euclid, I know that B must be less than A. If it was equal, I would have returned. Since I know that it is less, I can assume that this is true by induction, or this is correct by induction. Thus, it returns the greatest common divisor of B and R. And we know that the greatest common divisor of B and R is equal to the greatest common divisor of A and B. So in both the base case, Euclid returns the greatest common divisor, and the recursive case, Euclid returns the greatest common divisor. Okay. Is that questions? All right. So if you're going to attempt a bonus question on the assignment, think broad strokes. Don't reproduce these proofs. Just maybe point out some commonalities between Slowclid, the assignment question, and Euclid's algorithm. Show where they do the same thing. That's sufficient. Yeah. 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 So it returns, and again, it's because we have a solid base case. The base case works. And the base case is when the remainder is 0. And we've shown that, well, this, we can assume this works, and we've also shown that this is the same as the answer to A and B. Yeah.
R is equal to greater than B. So is that always going to happen at 1 and 1?
No. So whenever R is equal to 0. So it's not necessarily 1 and 1, but that's just the easiest way to show that it terminates. Yeah. So it can be, it can be, 75 and 25. Yeah. Anything that gives a 0 remainder. But in the worst case, if we get down to 1 and 1, it definitely returns. So that's the argument. Yeah. Other questions? Okay. How long does this take to execute? All right, we got 15 minutes. So we've shown that it's true. So what we're going to do is we want to count significant operations. So we're going to count this mod operation. And essentially, the mod operation is equal to the number of calls we make to Euclid, right? Every time we make a call, we execute this mod. So we're going to, we'll run through an example and count that, and then we'll prove it more generally. So for our Euclid 7545, we're going to define a function MAB is the number of times this mod line is executed. Okay, so A and B are our input, so we will, yeah. All right, so we'll run through this example and count it. So I make one call to this mod function here. R is not 0, so I'm going to make another call to Euclid, which means another call to the mod function. So now I've called it twice. R is still greater than 0, so I make another call to Euclid. And at this point, I make my last call to the mod function. R is equal to 0, so I simply return B. So in this case, I made 1, 2, 3 calls to the mod function, so we can say that, oh, and I possibly even have written it here already. Yes, so this function M7545 is equal to 3. Okay. So now we want to compute this more generally or bound it. So we can start by doing just a very loose bound, which means that, easy analysis, loose bound. So what's the most this could ever be executed is the same as the most number of calls we make to Euclid. So one thing that we do know is that B must be at least 1, and every recursive call I make, this B must be reduced by at least 1 because the remainder is less than B, which means that in the worst case, I make B recursive calls. Okay, that's not super good. If B is 1,000,000, maybe that's not the greatest, but we can do much, much better than that, actually. So that's the easy analysis. Now the hard analysis based on the Fibonacci sequence. Okay, so to see why we use the Fibonacci sequence, let's take a look at our algorithm and look at all of the different inputs that we use as when we make our recursive calls. So we start with 75 and 45. Then we make a call to 45 and 30, and then 30 and 15. And if I look at the sequence of arguments here, and I get rid of the repeats, then there's something a little telling about this sequence. For instance, I can write 45 is equal to 30 plus 15. And I can write 75 is equal to 45 plus 30. So if we look at the sequence of arguments, it seems to happen that, or if we looked at them in reverse from lowest to highest, then they kind of have a Fibonacci thing happening, right? So this number is equal to the 2 previous ones. This number is equal to the 2 previous ones. And this holds more generally, but it's actually an inequality. Yeah. All right, so. All right. What we want to show then is that we're going to prove lemma 2, which is that given that my call to Euclid AB makes M recursive calls, or M calls in total, I call the mod function M times, then it must be that A is at least the M plus second Fibonacci number, and B is at least the M plus first Fibonacci number, right? Which means that the inputs are going to basically shrink a lot faster. So does this mean M is large or small? We'll answer that question, but hopefully it's a little bit obvious. again, the idea is based on this linear equation because Q, we assume that A is greater than B, so Q must be at least 1 in this algorithm, which means that A is greater than or equal to B plus R. So it's like Fibonacci, right? Except in this case, A might be even larger. Okay, so if we can prove that, for instance, B is at most f of n minus 1 and R, or sorry, B is at least f of n minus 1 and R is at least f of n minus 2, then we can show that A is at least f of n. And then we can kind of bound the running time based on how many Fibonacci numbers there are in the sequence. All right. Yeah, so that's essentially what I just said. Okay. So we'll do induction on the size of M. So if M is equal to 1, that means we made one call to Euclid, one call to this mod, R was equal to 0, and then we returned. So yeah, in this case, yes, M, so this is f of M in some sense, which is equal to f of 1, which is equal to 1. So then I will argue that B is at least f of 2, and then A is at least f of 3. Hopefully that makes sense. B is at least f of 2. Well, f of 2 is simply 1. B must be at least 1. So that's true. And A is greater than or equal to B plus 1, which is equal to f of 3. So yeah, so all right, we'll go with that for now. This might be erroneous, but I think the actual argument's a little more complicated. I skipped some steps because if A and B are equal, then it's sort of trivially true. So we're going to proceed with this assumption that A is at least as big as, or at least as big as B plus 1. Okay, so our base case is true. So now we want to prove it for M at least 2. So yeah, so we're going to make one call to the mod function. And then in our recursive call to Euclid, we make M minus 1 recursive calls. Okay. So now our inductive step, we're going to assume for any recursive call where this MBR is equal to M minus 1, that is, we have M minus 1 calls to this mod function. We will assume that, right, we're just B and R are the arguments into this call to Euclid. So I substitute B for A and R for B. So I get the assumption that B is at least f of M plus 1 and R is at least f of M because it's on M minus 1. This is, again, I told you a lot of detail here to absorb. Hopefully you're kind of getting the broad strokes of it. Okay, so that's my inductive hypothesis. And if that's true, well, I know that A is equal to Q times B plus R, which means that A is at least B plus R. So, I mean, all that's left to show is I want to use my inductive hypothesis, which already gives me that this is true. And I want to use that to prove that this is true. Well, if A is at least B plus R, which is at least f of M plus 1 plus f of M, then A must be at least f of M plus 2. Okay. Almost finished. So we've shown that it has this Fibonacci sequence sort of thing going on. So how many recursive calls do we make then? Well, we know this is true. So now we want to bound this number. Yeah, so our claim is that this is at most log of, and I used the wrong Greek letter here. This should be phi. I don't even remember which Greek letter this is. But if you recall from our work on the Fibonacci sequence, the closed form of the Fibonacci number used one of the roots to, or both of the roots to x squared equals x plus 1. So this is a value for x that makes this true. And we're going to use that to bound the runtime of Euclid. This is approximately 1.6 something, something, something. Okay, so to prove this, we will say, well, if A is equal to B, then it's true because we make one recursive call, one call to the mod function. So that's equal to 1, which is less than or equal to 1 plus the log of whatever B happens to be. In the other case, we'll say that A is greater than B. So this is equal to M. And we have that B is at least the M plus first Fibonacci number. And we can prove, we're not going to, but we can prove that it's equal to phi to the exponent M minus 1, or at least that big. So we have this inequality. So we take the log of both sides, and I get log of base phi of B is at least M minus 1, right? So the log of phi to the M minus 1, I take the log of it with base phi, I get M minus 1, right? And then I do a little bit of algebra and I see that M is at most 1 plus log of B, essentially, using the golden ratio as the base of the log. Okay, so that is to say it runs pretty quickly. Binary search runs quickly. I mean, it depends how big B gets, I suppose. So this is not quite tell the whole story, but it tells enough of the story for today. All right, questions on that? A little rough, eh? So next class, we will talk about things like merge sort, and I don't know if we go over anything else, but I will have some. What do I have? Oh, I got some nifty little programs to show you. So it'll be a slightly more entertaining. There'll still be some math involved, but I'll leave that for today, and I will see you guys on Friday.